In section 2.3, we're taking a look at how to use algebra to evaluate limits, how given a formula for a function, we can calculate what a limit is. Now, your textbook calls this evaluating limits using limit laws, and we'll be using some of those. I've sort of modified the title of the section here to really emphasize that we're using some algebra to evaluate our limits. Now, I'm going to cover the same content that's covered in your textbook, but I'm going to do it in a slightly different order than your text. So I encourage you to be reading your textbook as you're working through these video lectures. Don't just use the textbook to flip back through it when you get confused. Actually, reading a math text is an important skill for you to be developing as you work through the calculus sequence. So I do encourage you to read the book. And if you find it too time-consuming, read part of it. Pick a part of each section to read. Just want to give you a heads up that the order in which these topics are covered is going to be a little bit different in the lecture videos than from this section. Okay. I'm also going to introduce a vocabulary word that your book doesn't introduce you to yet, and that's continuous. I'm going to tell you what it means for a function to be continuous. Your book is going to be using this principle without using that word, and then when we get to section 2.5, that's all about continuous functions. But here's what it means. We've actually seen it before. As we looked at a bunch of graphs, oh dear, this marker isn't very good. This one's better. Okay. As we looked at a bunch of graphs, we very often were concerned with what happened at places like this, where something weird happened, where there was a jump, or maybe a place where there was a hole in the graph like here. But most of the time, we've got stuff like this, where nothing weird happens, and where what we get is exactly what we expect, so that the answer to what's the function value and what's the limit are exactly the same. When that happens, we say a function is continuous there. So, a function f of x is continuous at an x value a if what we get, which would be the function value at a, is what we expect, which would be the limit as x approaches a of f of x. I remember this definition by that informal way of saying it. What we get, that's just the function value. What we expect, that's just the limit. Now, obviously, for this equation to be true, the function value has to exist. The limit has to exist, and they have to be the same. Okay, but what's nice is if I know I'm working with a continuous function at a point where that function is continuous, and I'm asked to evaluate this, all I have to do is plug into the function because the limit is the same as the function value. That's really nice, okay? So how do I know that? Okay. Well, right now I gave you the definition for what it means to be continuous at just a single x value. And obviously that would have to be an x value in the domain because I've got to be able to plug it in. We would say that f is continuous on its domain if it is continuous. I'm just abbreviating continuous here. If it's continuous at every point in its domain. Now, that means if I know if I have a continuous function on its domain, and I'm working at a point in its domain, I'm going to evaluate the limit by plugging in. So, that would make it really useful to know what sorts of functions are, in fact, continuous on their domains. And I'm just going to state two really important facts. Fact 1. The following types of functions are continuous on their domains. Okay, now this is going to be almost every type of function that we're used to working with. But if you think about it, that shouldn't be much of a surprise, because the functions that we're used to working with don't do a lot of weird stuff. And when something weird happens, it tends to be at a place where the function isn't defined. Okay. So constants, linear functions, so that would just mean if the graph is a line, power functions, so things like y equals x squared, y equals x cubed, etc., etc. Polynomials, so I could have 3x squared plus 5x plus 2. I could add together some powers and some constants and build a polynomial. That's going to be continuous. Rational functions. Rational functions are just fractions where the top and bottom is a polynomial. So this would include negative powers of x. Something like x to the negative 2 is the same as 1 over x squared. 1 is a constant polynomial, x squared is a polynomial, so this counts as a rational function. Okay. Roots. Okay. Algebraic functions. Algebraic functions are functions that I can build out of polynomials and roots. So I could have something like f of x equals the square root of x squared plus 5 over x minus 2. The top is the square root of a polynomial, the bottom is a polynomial. I built this out of polynomials and roots by just using some combination of arithmetic and function composition. Okay, let's see, we've also got our trig functions. We've got exponential functions. We've got log functions. We've got inverse trig functions. And we've got the absolute value function. So just about everything that we're used to working with. Now, there are plenty of places where there are still going to be interesting limits to look at, because, for example, with this algebraic function, 2 is not in the domain. That's going to be the most interesting limit for us to take a look at and see, does that exist, and if so, what is it? Okay. But for any of these types of functions, they're going to be continuous on their domains. So if I can just plug into the function and I get a number, and it's one of these types of functions, that number is the limit as I approach the x value that I'm plugging in. Pretty cool. Okay, rather extensive list. So extensive that I've got to erase it. That's the downside of having this smaller board here. I'm erasing all the time. But we need room for fact 2. And that's that any function built out of continuous functions using arithmetic and or composition is continuous. Now, what does that mean? Well, if I were to take f of x equals e to the sine x. Sine x is a trig function. That was on our list, so it's continuous. E to the x is the exponential function. That was on our list, so that's continuous. This is just a function composition because I'm taking sine of x and plugging it into that exponential function. So this function is continuous on its domain. G of x equals the square root of x times the natural log of x. That's a root, that's a log. Each of those is continuous on their domains. Here I connected them with arithmetic. I connected them by multiplying them together, but this function is continuous on its domain. So essentially, if we work with the functions that we're used to working with, the interesting limits are going to appear at points that are not in their domain. Okay. All right. So with these two facts, that gives me my first method of evaluating limits algebraically. If f of x is continuous at a, evaluate the limit as x approaches a of f of x by plugging in a. And that would be, of course, to get f of a. All right, here's an example. Let's say I wanted to take the limit as x goes to 2 of x squared. Well, that's just a power function. That's continuous. 2 is in its domain. So this would be 2 squared. That's 4. Okay. Let's say I want to take the limit as x goes to 3 of x squared plus 5x over x minus 2. Okay. Now this is a rational function. Rational functions are continuous on their domains. 2 wouldn't be in the domain, but I don't care because I'm taking the limit as we approach 3. So this would just be 3 squared plus 5 times 3 over 3 minus 2. That's 9 plus 15 is going to be 24 over 1. So that's just 24. So this is the easiest way that we have of evaluating limits. Limits like this aren't particularly interesting, so we won't spend a whole lot of time practicing this because it's just the same as evaluating a function. But very important that you remember to check for this, because sometimes you can spend a lot of time trying to figure out what do I do when all you had to do was plug in. The more interesting limits, we will have more to do because we won't be able to do this, but often what we'll be doing is we'll be doing some algebra until we get to the point where we're able to evaluate the limit that we've gotten to by simply plugging in. So that's going to often be our goal.